Hey, Come30, welcome to topic 5 of Unit 5, pOH and pH calculations. It's really important that you've done your topic 4 practice questions. If you haven't done that, go back and do those before starting here. So pH and pOH are used to simplify really small numbers, like we often see with H plus and OH minus concentrations. A change in one of a pH is actually a tenfold effect because pH is on a logarithmic scale. So let's consider three acids. We've got a pH of an acid with 6, a pH of an acid with 5, and then an acid with a pH of 4. From this to this is a 10 times effect, and then from 5 to 4 is also 10. So from the acid with a pH of 6 to the acid with a pH of 4, this is actually 100-fold. It's 100 times stronger. An acid with a pH of 4 is 100 times stronger than an acid with a pH of 6. And this is why small differences in pH actually make a large effect in reality. So we can think about something like the ocean acidification. The oceans are slowly acidifying because carbon dioxide from the atmosphere is dissolving into the oceans, making a really weak acid called carbonic acid. But as it does that, it changes the pH. So we might think of the ocean being something like 6.37, and it's going down to let's say 24. Well, that's not a huge difference. The problem is at the rate that it's happening, animals can't adapt to it. So just imagine, instead of weighing, let's say 150 pounds, let's just take your body mass and increase it by 20%, right? So a small pH change, even a pH of 1 is a 10 times effect. We're not going to be able to do that. But even a small change, let's say that you weigh now 30% more. So when you take this number and you figure out what a change of 30% on 150 would be, and we're talking this is happening in just a couple of years, 150 times, you all of a sudden become 195 pounds, right? So that's a huge difference, and that's just your weight. But animals are trying to breathe in this water or move about it or do different biological functions. This is a gigantic pH chart. You can kind of zoom in and see some of the things in here. It has foods that we eat. So you can see lemon juice here, or hot sauce has a pH of 3, depending on what it is. Peaches are slightly acidic, a pH of 3. Battery acid is all the way down here, kind of at, here we go, right here at a pH of 0. It's so strong that it's basically off the chart almost. And then we have some bodily fluids are on here, right? So our saliva is slightly acidic. Dry skin is about a pH of 7, so it's neutral. Blood and breast milk, all sorts of weird things on here. It's a really fancy pH chart. And we can see that it goes from 0 to 14, neutral being 7. So acids have anything a pH of less than 7. Bases have a pH of greater than 7. So 7.01 would be considered slightly basic. Essentially, it'd be neutral. Anything like 6.99 and smaller would be acidic. Okay, strong acids are right on the very bottom of the pH scale. Strong bases are right on the very top of it. Okay, so high pH, strong base. Low pH, very low pH, acidic. Okay, close to 7 is neutral. There are some super acids or super bases that fall outside that range, but they're not common enough to talk about. So pH is the same idea as pOH. When we're trying to figure out the pH of something, all we're going to do is take the negative log of it. Okay, so pH is equal to negative log concentration of H plus. pOH, the exact same thing here, is equal to negative log of OH minus. Together, they add up to 14. So we can think of a neutral solution. In a neutral solution, we know that concentration of H plus is equal to concentration of OH minus. Both of these numbers are 1.0 times 10 to the negative 7. Turns out when you take negative log of 1.0 times 10 to the negative 7, you get 7. So then you do the same thing here, and you get 7. So in a neutral solution, both of these values are 7, and they add up to 14. When you increase the amount of acid, let's say that you increase the amount of acid to negative 10, negative log of 10 to the minus 6 is 6. So that must mean that the pOH goes to 8, because it always has to add up to 14. Okay, so as the pH drops, the pOH rises. As the pH rises, the pOH drops. They're really the same thing. So if we imagine a pH scale. So we've got 7 in the middle, 0, 14. This is our strong acids, strong bases. A pOH is just an exact opposite measure. So we got strong bases down here, strong acids at the top, and neutral in the middle. So just flipped. To calculate the concentration from pH, the concentration of H plus or OH minus from a pH or pOH value, we just take 10 to the power of negative whatever we're talking about. So in your calculator, it will have to be the second function of your log button, but you can just go 10 to the power of negative whatever number you're given. So let's say a solution has a pH of 2.35, we'd say 10 to the power of negative 2.35 is equal to the concentration of H plus. Pretty straightforward there. This slide is nice because it shows how to move from one to the next. So just highlight slide 73 so you can use it when you're doing your practice questions. We can see that we can move from H plus to pH by taking the negative log of that H plus value, pH back to H plus by 1 times 10 to the power of. That doesn't really matter, so we just cut that out. Just take 10 to the power of negative pH. We can move from pH to pOH by using 14 minus what we have to get to the other one. And then we can go from pOH to OH minus using the same idea as H plus on the top. And then lastly, we can move between OH minus and H plus. We learned this yesterday because we're using KW. So KW over H plus is equal to OH minus, and we can see that right here. That's our KW value. It's always the same, 1.0 times 10 to the negative 14 divided by H plus gives us OH minus, and vice versa for the way back, okay? So this is a nice little slide until you get these calculations in your head. You will not be given these formulas on an assessment. So pH of acids and bases. When we do these, we have to write the ionization equation, determine the H plus concentration using a Ka calculation if we've got a weak acid. If we've got a strong acid, then the concentration of H plus is equal to the concentration of the initial acid, right? So it breaks down 100%. 100% forms those ions. So let's take a crack at this one. A solution has a concentration of 3.54 times 10 to the negative 4 moles per liter. What is the pH? What is the pOH? And what is the OH minus? The answer is on the bottom of the slide. If you want to pause it and try it yourself, you're more than welcome to. But here's how we're going to do it. So pH, we should recognize pH is equal to negative log concentration of H plus. It tells me the concentration there, so I'm just going to go negative log bracket 3.54 times 10 to the negative 4 moles per liter, which works out to being 3.45. Okay, make sure you're using brackets around your terms when you're using logs. You want to make sure that it applies to that whole thing, not just the base 3.54. Okay, what is the pOH of the solution? There are two ways that we could do this. We could go KW divided by, oops, try this again. For B, OH minus is equal to KW divided by concentration of H plus. So we could do that calculation, or we can recognize that the pOH would be 14 subtract pH is equal to pOH. So 14 subtract 3.45, which is equal to 10.55. Okay, so either one of those calculations. With this one here, we'd have to finish it by going negative log. I'll write it like this: pOH is equal to negative log of OH minus. So it's 2 steps, and that's generally why I avoid it. I also try and avoid putting scientific notation into my calculator as much as possible. It takes longer, and I'm more likely to make a mistake. And then finally ask, what is the concentration of OH minus? Well, if we did this step here, we'd already have this answer. But we can just quickly figure this one out by going concentration of OH minus is equal to 10 to the power of negative pOH, which is equal to 10 to the power of negative 10.55, which is equal to 2.81 times 10 to the negative 11. Now this, remember to stick your unit on here, and this makes sense to me. Why? Because I know this is an acidic solution. I can see that 3.5 times 10 to the negative 4 is greater than 1.0 times 10 to the negative 7. So I've got more H plus than in a neutral solution, which means I must have less OH minus. And I can see that this exponent here is much less than negative 7. Therefore, there's less OH minus. So which one be which is what I expected in an acidic solution. Okay, welcome back. We are going to figure out the pH of a 0.15 molar solution of sulfuric acid. First, we're going to begin by writing out the ionization equation for sulfuric acid. Now, H2SO4, we're going to consider H2SO4 to be a diprotic strong acid, meaning that when it protonates, it produces 2H plus and SO4 2 minus. Now, this is not strictly true. It actually goes through two protonations. So H2SO4 breaks down into HSO4 minus and H plus, and then produces HSO4 decomposes into SO4 2 minus and H plus as well. But this ion here is strong enough that it essentially does do this. We can treat it as another strong acid. So if that's the case, then really when we add these up, because they're on opposite sides of that arrow, it's something called Hess's law. They cancel out. These add up because they're on the same side. So we get H2SO4 produces SO4 2 minus and 2H plus is what we see over here on the left-hand side. So we should recognize that the concentration of the acid is equal to the concentration of the H plus, but in this case, because it produces 2H plus, it's going to be 2 times 0.30, which gives, and then we don't care about that. So the concentration, the pH of the solution is equal to negative log concentration of HA, which is equal to, H plus, pardon, which is equal to negative log of 0. Sorry, I just made that mistake up there. I'm fixing it. There we go. Which is equal to 0.523. And we can see that this is very strong, right? So a fairly weak solution, something that we consider it to be weak here at least, produces a really low pH. Why? Because every single ion of that sulfuric acid or molecule of that sulfuric acid will give off some hydrogen. Not only some hydrogen, but twice as much. Okay, so a pH calculation for a strong acid is quite straightforward. On this slide here, we have a calculation for aniline, which is a weak base. So anytime we see anything that ends in INE, I call this aniline, but it's probably aniline. We're going to be using our reference book to figure out what that formula is going to be. So aniline is in here under the bases. Okay, so aniline at the top there, C6H5NH2. So C6H5NH2 aqueous, and we should recognize this as being a weak base, which means we need to use the Bronsted-Lowry definition of ionization. So C6H5NH3 plus aqueous and OH minus aqueous. We can't just do an easy, straightforward pH calculation or pOH calculation on this one because the concentration of the base here is not equal to the concentration of the hydroxide ion. Only some of it ionizes, and that's based on its Kb. So we're going to write the Kb value up here. The Kb value for this is 4.3 times 10 to the negative 10. And just as we did Kb calculations in top 4, we're going to do that again, which is going to give us eventually the concentration of OH minus. I can figure out the pOH of that using negative log 14 minus the pOH would give me the pH of the solution, which is what the question is asking us for. So we're going to start by writing our ice table. So this is 0.00675. This is going to be dashes. This is going to be 0 to start with, 0 to start with. This is going to be negative x, 0.00675. Dashes all the way down. We're going to increase by x, increase by x. So we get x and x. So we're going to make that same statement that we always do. 0.00675 subtract x is approximately, let's try to make a better one. That's still not much better. There we go. 0.00675. So we're going to solve the Kb for this. So Kb is equal to the concentration of C6H5NH3 plus OH minus over C6H5NH2. So this is 4.3 times 10 to the negative 10 is equal to x squared over 0.00675. So I'd multiply the, so I'm going to say this but not write it. So 4.3 times 10 to the negative 10, I'll put that into my calculator, multiply by 0.00675. So now I've got x squared is equal to 2.90. So I'm going to square root my answer, and I get 1.7, x is equal to 1.70 times 10 to the negative 6. And right now I can make an assumption that my answer is correct here. Why? Because I know this is a weak base. So it should have slightly more hydroxide than a neutral solution. Remember, a neutral solution has 1.0 times 10 to the negative 7. This is essentially 1.0 or 2.0 times 10 to the negative 6. So slightly more, which is something that I would expect in a weak base, right? It's going to be close to that mark, not significantly stronger, but stronger than a neutral solution or more than a neutral solution. All right, so I got my x, but I haven't answered the question. I'm going to move into green here. The concentration of OH minus, now we know, is equal to 1.0 or 70 times 10 to the negative 6. pOH is equal to negative log of OH minus. Now, if you haven't cleared your calculator, excellent. All we're going to have to do is negative log, answer equals 5.76. And you'll notice that that is not the answer down here. Why? Because we've solved the pOH. So one last calculation for us to do here. pH is equal to 14 minus pOH, which is equal to 14 subtract 5.76, which is equal to 8.23. Before I'm done, is this a reasonable answer? Again, it tells me that it's a weak base. From my reference book here, I know that aniline is a weak base, which means that it should be somewhere close to that 7. Higher than 7, but around that 7, and 8.23 certainly in that. Okay, this example is a little bit different because we're given a pH and we're actually asked to solve the Ka, or the acid dissociation constant. So niacin, one of the B vitamins, has a molecular structure shown below. A 0.020 molar solution of niacin has a pH of 3.26. What is the acid dissociation constant for niacin? Now, I could take this formula or this model and figure out how many carbons and hydrogens are involved, but I'm just going to use the generic form of acids, which we should recognize as being HA. So HA represents niacin aqueous, decomposes into H plus ions and A minus ions. Okay, so we're going to tabulate our information. It tells us that it's a 0.20 solution. We've got none of this and none of this. We're going to do the same sort of procedure that we always do. X and X plus, and then X and X. And then we're going to say 0.020 subtract X is approximately 0.020. Now we're stuck, because normally we'd take this and put this into a Ka expression and solve based on that Ka, but instead we're given a pH. So is there anywhere that I could use that pH? What is pH related to? Well, it's related to the concentration of hydrogen. So if I reverse engineer the pH to figure out an H plus value, remember H plus is equal to 10 to the power of negative pH. So this would be 10 to the power of negative 3.26. So when I do that, second function, function log negative 2.36, or sorry, 3.26, I get 5.450. So this is 5.50 times 10 to the negative 4 molarity, which I expect, if this is an acid, I would expect the concentration of the H plus to be greater than 1.0 times 10 to the negative 6. I can see it's a relatively strong acid. It's not at that 6 or 5, but it's actually at 3. So it's quite a bit stronger than what we've worked with so far. Anyways, now that I have that, if I know that X is equal to, in this case, H plus 5.0 times 10 to the negative 4, Well, that must be also the same value for this. So 5.50 times 10 to the negative 4. And I have my equilibrium value of the HA, so it's just that. So we can write this now as Ka is equal to the concentration of H plus A minus over the concentration of HA. So we get 5.50 times 10 to the negative 4 squared over 0.020, which works out to being 1.5 times 10 to the negative 5. Okay, remember that acid dissociation constants have no value, so we're done with just that. For the next two examples, this one here and the one that follows, we've done questions like these already. So I'm going to get you to pause the video, try it on your own, and only use the video if you get stuck. The answers are on the bottom of the slides. Welcome back. This example is a little bit different. It asks what concentration of ammonia is needed to produce a solution that has a pH of 11.17 if the base dissociation constant for ammonia NH3 is 1.8 times 10 to the negative 5. So we're going to start by writing the ionization equation for this. So NH3 aqueous, this is a weak base, and we need to put it in water, and we use that Bronsted-Lowry definition of weak bases. So NH4 plus and OH minus aqueous. And in this one here, it's actually asking this number here, which we don't know. So we're going to symbolize that as X. It would have decreased by some number here. And then we have X minus some number. And I know this is a really strange way of doing it. Let's actually use this negative Y, and then we got 0. These are dashes all the way down, 0 and 0. And then we're going to get positive Y here, and then we get Y and Y. So we can see that we have two variables. The only reason why we can solve this is we've got one other piece of information. It tells us the pH. pH for us is kind of useless. So what we're going to do here is we're actually going to convert this to pOH, because when we move from pH to pOH, it tells us, or eventually can tell us, the concentration of the hydroxide ion, which is in there, which we know as being Y. So then we can work backwards and solve this. This would be X minus Y. So we will get pOH is equal to pH, oops, just kidding, 14 minus pH, which is going to give us a pOH of 14 subtract 11.17, oops, 2.83. So a concentration of OH minus would be equal to 1.48 times 10 to the negative 3 molarity. So we know this number here is 1.48 times 10 to the negative 3, 1.48 times 10 to the negative 3. And even though we know that this is X minus Y, we can write that same statement that X minus Y is approximately equal to X. So we're just going to ignore this Y part here. So now that we have all that piece of information, we can write a Ka. So Ka is equal to the concentration of NH4 plus OH minus over NH3. So we know the Ka. So that's 1.8 times 10 to the negative 5 is equal to 1.48 times 10 to the negative 3 squared over concentration of NH3. So I'm running out of room here a bit, but I'm going to walk you through how to solve this. We're going to simplify the top, get that into a single number, then we're going to multiply. When we are trying to solve a 3-variable equation like this, where we have A is equal to B over C, that's the same as, that is equal to C is equal to B over A. So these two things just flip spots. So what we're going to get here is the concentration of NH3 is equal to 1.48 times 10 to the negative 3 squared divided by 1.8 times 10 to the negative 5. So I'm going to write that out. So concentration of NH3 is equal to 1.48 times 10 to the negative 3 squared over 1.8 times 10 to the negative 5. So the concentration of NH3 is then, I'll put this into my calculator just to prove it. So we get 1.48 times 10 to the negative 3 squared divided by bracket 1.8 times 10 to the negative 5 gives me 0.12168 and a whole bunch of 8s and then a 9 at the end. So we're just going to simplify that to 0.12 molarity. So if we have a 0.12 molarity solution added into water, we'll actually get a solution with a pH of 11.17. So there are complex cases that exist in acid equilibrium, but these are not going to be part of our course. This is just simply something you might see when you transition to post-secondary. So I just want to expose you to it. So if you feel as though you've gotten enough information already for one day to get on with that practice, go do that right now. If you want to see a little bit more, stick around and I'm going to show you when we need that quadratic equation. So in some cases, the ionization value of weak acids is high enough and the concentration of the initial acid is low enough that the dissociation is actually a factor in it. So instead of thinking a billionaire losing a couple of dollars, think of someone having $1,000 and losing 100. So in this situation, HA minus X is significant enough that we have to factor in X. And there's a quick check that we can do. If the ionization, percent ionization, is how much breaks down, and it is a factor of H plus, concentration of H plus over concentration of HA. And if it's greater than 5%, then the X that we usually just ignore in the ICE table is significant. So we can do this quick little check here. So remember, if we have HA breaks down into H plus and A minus, usually we write this as some number minus X, and then we just write that some number anyways, right? So we just generally call this HA in the end. It's the same value there. And this becomes X and this becomes X. When we rearrange this and solve, if we have the Ka, we get exactly this, because normally we have Ka is equal to X squared over HA. We can rewrite that equation so that HA and X represents X, this is X squared, but X represents H plus. So if we can isolate X, so we take the square root and blah, 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 we get this formula here. So the square root of Ka multiplied by HA over HA is essentially the percent ionization value. And if you want to see a little bit more on that, just pop into class and ask me about it. I'll show you how I derive that formula. But we can use this formula to see if we need to use the quadratic expression, right? So then we'll go through a different procedure, and we'll see this on the next slide. We've got a complex example here, and remember, this is not going to be part of your assessment. It's just simply something that you might encounter in the future, and it's an interesting sort of case to look at. So first thing that we're going to do here is check to see that the ionization value of formic acid is less than 5%. So we're going to do that by taking the square root of Ka multiplied by the original concentration of the acid. So we call that HAI, so for initial, over that. So remember, this is really just the percent ionization formula. So percent ionization is equal to concentration of H plus over HA. We can sort of multiply it by 100 here. So we can easily imagine that it's the same as taking a grade on an assessment, right? So the score that you got over the possible highest score. So how many ions do we have over the possible highest amount of ions? So in the reality, this would be multiplied by 102. So we take 1.8 times 10 to the negative 4 multiplied by 0.00125, the square root of that over 0.00125 multiplied by 100. Now that square root only applies to the numerator, not the denominator. When we do this, we actually get a value of 37.94%. So this means that HA minus X, when we use that table, the ICE table to solve, X comma X is equal to a significant number. It's going to make a big enough impact. So if we imagine that as that bowling ball or a water bottle being handed inside the vehicle, essentially now we've got a motorbike and someone hands them a Culligan jug. There's going to be a difference, a large enough difference, or someone that has $10,000 losing $1,000. There's going to be a difference between the initial amount and the change. So we're going to take our equation now. So we're going to write HCOOH aqueous, ionizes to form H plus aqueous, and HCOOH or HCOO minus aqueous. Now, to save a little bit of room here, we should recognize that it's going to be initial plus change. So in the end, this is going to be 0.00125 subtract X. This is going to be X, and this is going to be X. So that gives us a Ka is equal to concentration of H plus HCO minus, that's the forming ion, over the original concentration. So we're going to get 1.8 times 10 to the negative 4 is equal to X squared over 0.00125 subtract X. When we multiply this out, so we're going to take that 0.00125 multiplied by 1.8 times 10 to the negative 4, which gives us 2.25 times 10 to the negative 7 subtract 1.8 times 10 to the negative 4 is equal to X squared. We want to get this into our quadratic equation formula. So we want AX plus BY plus C equals 0. So we're going to move that X squared over and put that first. We get X squared plus, so we're moving, really we're stacking everything on the right hand side then reversing it. So we get plus 1.8 times 10 to the negative 4 subtract 2.25 times 10 to the negative 7. We're going to use the quadratic equation to solve this. So we get X is equal to negative B plus or minus the square root of B squared minus 4AC all over 2A. So we'd get X is equal to negative 1.8 times 10 to the negative 5 plus or minus the square root of 1.8 times 10 to the negative 5 squared, subtract 4 times 1 times 2. That's negative, by the way, 2.27 times 10 to the negative 7. Sorry, I'm kind of running out of room here, hey? All over 2 times 1.8 times 10 to the negative 5. So when you solve this, you actually get two numbers. The reason why is because a quadratic has two roots. Essentially, we're figuring out where this equation crosses the x-axis. So it looks something like this. It turns out that this value here is 0.00. One of the values of x is 0.003928, and then the other one here is negative 0.00572. Now, obviously, I have not drawn this to scale, but it has those two numbers. And we can easily see that we're going to toss out 1, because what does X represent? X represents the concentration of the H plus ion right here. It represents that. So can we have a negative number? Of course not. So we get X equals, in this case, either negative 0.005 0.072 or 0.0003928. We toss this because we can't have a negative. We can't have negative. So this becomes our concentration of H plus. So we're going to write that as concentration of H plus is equal to 0.0003928. So I'm going to continue this up here because it asks us really for the pH. So all that work for the pH. pH is equal to negative log concentration of H plus. In this case, because I'm running out of room, this is going to be negative log of 3.98 times 10 to the negative 4, which gives us 3.41. And that's unitless. So 3.41. In purple, again, because I'm out of space here, I'm going to answer B. So what is the percent ionization of this formic acid at this concentration? So percent ionization is equal to H plus over HA multiplied by 100. This here, this does not work. This is not a percent ionization equation. That is simply a check because that assumes that the X value is insignificant. We know that it is. So now that we have an actual value for our H plus, which is 0.0039, oh, I missed a zero there. So 0.0003928 over 0.00125 multiplied by 100, and we get 31%. Okay. So that's a difficult question. Obviously, you're not going to get that on anything in this class, but you can see how the same principles and the same steps apply to it. All right, Chem 30, that is it for topic number 5. As always, if you have any questions, email me. Otherwise, have a great night.